So now we're going to look at the inequality. Notice the only thing that's changed between the equation that I was using up here and this inequality is that it's no longer an equal symbol, but this time it's a less than symbol. And it could be any of these four symbols over here for an inequality. To do it, to prove it algebraically, the process is exactly the same. I'm going to plug in the 1 and the 3. The 1 that I'm going to plug in is going to go in for the x value. The 3 is going to go in for the y value, and I'm going to determine if the resulting statement is positive or is true or false. So I plug in the 3, I plug in the 1, and now my mathematical statement says that 3 is less than 3. Well, last time it was a true statement because 3 is equal to 3, but this time it is actually false. It is not a solution. Because 3 is not less than 3. I'm going to do the same thing for the 0, 0. I'm going to plug in 0 is less than 2 times 0 plus 1. And this time I get 0 is less than 1. And this time I get a true statement. So when I changed from an equation to an inequality, both of my truth values changed. My true value became false and my false value became true. So what's happening graphically? Well, if everything else is the same, the slope is the same, the y-intercept is the same, that means the linear equation is the same. The only thing that's different is, well, first of all, it's just a less than. So when it's a less than, according to the cowboy and the angel thing that we learned, the cowboy and the angel, because it's just a less than, we're going to have a dotted line. That's how the cowboy and the angel helps you. If there's a bar underneath either one of the inequalities, you'll have a solid line. So this line right here should be, let me see if I can get just the line erased. I'm going to hit delete and probably everything's going to go away. Okay, so this time I'm going to put the line up there. I'm going to make it a dotted line. Okay, whoops, that's definitely not in the right place. So let me try that again. I'm going to put the dotted line. I guess it's going to be right there where my arrow is. There we go. So I do need to put the dotted line. Now, the dotted line is going to help me out because it's dotted. What that means is that all of the points that are on the line are actually not going to be solutions. So that's what happened over here when we plugged in that 0.13. 13 is a point on the line, but since it was a point on the line, but the line itself does not contain solutions, that means that acts as a boundary line. It's going to be all the points up to the line, but not including the line. If we'd had the bar underneath it, then we would have made the line solid, and the 0.13 would have been actually a true statement, and it would have been part of my solution set. But so when it's less than or when it's greater than, like we see over here, we have less than or greater than. When we have either one of those, our line is going to be the boundary line. It is not going to contain solutions though. So then we found that the 0.00 was true. So this is kind of a cool thing. When we find out that the 0.00, which is this point right here, since we found out that that point caused my equation to be true, that tells us that any other point on the same side of that line, so that means all of these points over here, is going to make my equation true. So in other words, this will be the part of the line that I will shade. So my shading is going to be this side. Uh-oh, I'm getting really sloppy. I'm going to have to go back and erase any of that bled over the line, because it's just shading up to the line, but not on this side, just on this side. Not on this side over here. I don't know what you would call it, the top of it, or maybe kind of the top left, but rather the bottom right. Those are all of the points. These right here, all of these points are solutions. They will all make the equation true, and anything that we pick on this side over here will make the equation false. And just to prove the point, let's pick one over here. Let's just do a random selection. Let's pick that point right there, the point -1, 2, 3, 4. That's the point -4, 2. So if we plug that point into this equation, we're going to expect to get a false answer. I plugged in the point -4, 2, and 2 times -4 is -8. -8 plus 1 is -7. And this says 2 is less than -7. That's a false statement. Any other point over here, it doesn't matter which one. Let's pick this one. That's the point 1, 2, 3, 4, 5, 6, 7, 8, 2. We pick the point 8, 2 and plug it in, and we expect to get a true solution. So 8, 2 gives me 16 plus 1. 2 is less than 17, which is true. So that was just an extra way to verify that I've correctly shaded. I've shaded the correct side of the line. I picked a point on the line. This point right here was on the line, and it came out to be false. That's how I knew it should be dotted. And then I found a point that made it true, so that's how I knew which side to shade. You can remember that if it says less than or less than or equal to, these two right here, you're going to be shading below your line. And then the greater than or equal to, those are going to be shading above your line. So that's a quick glance and tell, but you should always do a plug and chug to verify that your shading is correct.